morning to all. Today we will talk about multi-stage amplifiers. When we talk about multi-stage amplifiers, let us see why should we have multi-stage amplifiers in the first place. Do we really need multi-stage amplifiers, or can I somehow design a single stage amplifier that has all the needed specifications? Is it possible? Let us see whether we can manage with a single stage amplifier. In that case, we did not study this particular topic. Let us consider a voltage amplifier. As we said yesterday, most of the time we are actually looking for a voltage amplifier. Now, what are the parameters we are looking for in a voltage amplifier? Again, from what we studied yesterday, you might be remembering, we talked about 4 types of amplifiers. We said the most common one is the voltage amplifier, and then we have current amplifiers. We also have transconductance amplifiers and also trans resistance amplifiers. We also said that the input requirements, or rather the ideal conditions for all these 4 amplifiers are very different. When we talk about a voltage amplifier, ideally we are looking for very high input resistance. We said why. Yesterday we discussed why. We saw that the equivalent circuit of a voltage amplifier, if you see at the input side we have a resistance Ri, and only if that Ri is much higher than the source resistance, we can get the entire voltage across the input of the amplifier. So therefore, in a voltage amplifier we must have very high input resistance. We also saw that a voltage amplifier must have very low output resistance. We also saw the reason yesterday. This is because of the fact that the voltage amplifier, we said, is a voltage controlled voltage source. In a voltage source, if we use the Thevenin equivalent circuit, the Thevenin representation, we have an open circuit voltage in series with a resistance. Now, any current which that is flowing into the load has to flow through this series resistance. Therefore, if we do not have a low output resistance, lot of voltage will get dropped across that particular resistance, and the load will not get the full, the amplified output. So therefore, in a voltage amplifier necessarily we must have very high input resistance, very low output resistance. Also we require high gain and let us say high bandwidth. The last requirement is not very often required. We also saw yesterday why. We said the 741 op amp and other op amps have become extremely popular even though they do not have high bandwidth. We said it is for the simple reason that for most of the applications, especially sensor applications, the frequency we are talking about will be most of the time typically less than 100 hertz and definitely not more than 1 kilohertz. So therefore, we are not worried about high bandwidth, but there are applications like video applications or even audio application where an op amp bandwidth may not be sufficient. Now, looking at these parameters of the voltage amplifier, we know from our study yesterday that all the above parameters cannot come out of a single stage amplifier. We know that when we, based on our discussion yesterday, we saw that most of the amplifiers have maybe one of the properties, not all. So therefore, we cannot manage a practical application with a single stage amplifier. We can almost certainly say that for any practical application we have to necessarily use more than one stage. Now once again let us take another block, which let us consider the 741 operation amplifier. Now we know that we can you can build circuits around say the 741 op amp, a voltage amplifier which is almost ideal. We know that if we build a non-inverting amplifier using the 741, the input resistance will be very high, it can be made several megohms. The output resistance can be made very low, say typically within say a few ohms. So we see that a 741 op amp, when we use it in the negative feedback circuit, we see that it possesses the kind of ideal parameters. Now what about this op amp 741? Is it a single stage or is it a multi-stage circuit in its construction? Now op amp is very much a multi-stage amplifier. Some of it was discussed by Professor Sharma, and if you see the inside circuit of an op amp, we see that it is a very complicated circuit, but you can divide the op amp into about 3 stages. This is 741. Most of the op amps which you get in the market has typically let us say about 3 stages. All of them would have an input stage which is a differential stage with high input resistance, high CMRR and high gain. Now that way the input stage can be designed to ensure that you have high input resistance, and the op amp being a high gain differential amplifier, the input is a differential stage. This may not be the case for some other amplifiers, and in a 741 op amp the input stage also has gain of the order of about 1000, slightly less than 1000. Now in a 741 op amp you have a second stage which is called a gain stage. Now in 741 this is a compensated op amp, rather it is a compensated gain stage, meaning internally a capacitor has been introduced between the let us say the collector terminal and the base terminal, and from our discussion yesterday we saw that in a common emitter kind of configuration, if you connect a capacitor between the collector and the base terminal, we said that particular capacitor gets multiplied by the gain. In a 741 internally they have introduced a 20 pf capacitor, approximately 20 pf capacitor, which gets multiplied by a gain of about 1000. So you get a highly compensated, meaning you have an extremely low frequency cutoff, rather cutoff frequency, high frequency cutoff frequency. In an op amp like 741 the cutoff frequency is 5 hertz. Now in some other op amps you might not have compensation, internal compensation. In a 741 this compensation has been done to ensure that when you use it as a negative feedback amplifier, under no circumstances it should go into kind of a positive feedback. Now in a op amp, once again all op amps would have a third stage, sometimes let us say the final stage, which is called the output stage. Now this particular stage is meant to drive an output load. Now 741 can drive a maximum current of about 20 milliamps. If you have to drive more current you need to add some extra discrete components, transistors at the end. So we see that an op amp is also a multi-stage, and you get this kind of ideal situation precisely by combining 3 very different stages. So in summary we can think of multi-stage amplifiers as very good options to get the desired amplifier specifications. Now typically they would have 2 or more stages, definitely 2, but most of the time it would have 3 or more. So another very important thing to remember, just like from the example of 741 op amp, is also that in a multi-stage amplifier the individual stages are not identical. In fact, these stages have been chosen with a purpose, each one with a very specific purpose. In the case of a 741 op amp, we saw that the input stage is designed specifically to provide very high input resistance and differential, it is a high gain differential amplifier with very high CMRR also. So that is the very purpose of the first stage, whereas the second stage does not have high gain, sorry, it does not have high input resistance, but it has high gain. Now its output resistance is also not that low, whereas the third stage in an op amp is very, very different from the first 3 stages. So we can say most of the time when you talk about a multi-stage voltage amplifier, it would definitely have more than 2 or more stages, and almost always the first stage would require large input resistance. This is to ensure that when you interface this particular multi-stage amplifier with a sensor, the finite, rather the high resistance of the sensor need not upset the performance. So if the input stage has very high input resistance, almost entire voltage would get developed across the input terminals. Now at the same time, when you talk about the first stage need not have high voltage gain, it need not be high. If you get it, is okay, but that is not the major requirement. The main requirement is to have very high input resistance. When you talk about the second stage in almost all multi-stage amplifiers, we see that there is no requirement to have a high input resistance, but that stage must provide very high voltage gain. So the main requirement as far as the second stage of a multi-stage amplifier in a practical situation, the main requirement is to have very high gain and it need not have high input resistance. Now again, coming to the final stage, the main purpose of that final stage is to interface with the output load. Therefore it did not have any voltage gain, it can be just a unity gain, but it must have low output resistance. Now before we consider a numerical example to illustrate what we said, let us look at another example which we discussed yesterday. Let us look at the public address system, which we are very familiar with. Right now I am speaking into a microphone and the output of that microphone is extremely small, definitely not more than 100 millivolt. Typically it would be about 50 millivolt, but unfortunately if you consider this microphone as a sensor, you would see that the source resistance is extremely high, typically the order of 100 kilo ohms or more. Therefore if I directly take the output of the microphone and connect it, let us say, to a common emitter amplifier, you would not get any input to amplify. So therefore in a public address system we see the same like what we saw in an op amp. Typically a public address system would have 3 or more stages, and in a public address system the scenario is slightly different. Now the first stage must take care of interfacing to the sensor, which is the microphone, and as I said, the microphone has very high source resistance and it gives you extremely small outputs. So what is done in a public address system is, the first stage would be a low noise preamplifier. Now that stage, the main purpose of that particular stage is to ensure that there is some amount of amplification and a fairly high amplification, but extremely with low noise. So therefore the preamplifier devices are very carefully chosen. They are very special devices which are low noise devices. And then the second stage in a public address system would be what is called, let us say, a post gain stage or a gain stage, and you might have 1 or 2. And as we are all aware, in a public address system occasionally you might take input from some other place, let us say from a cassette recorder, you might take output from a cassette recorder. Now the output from a cassette recorder is fairly high, much higher compared to the output from a microphone. So therefore in most of the public address system, what is done is the output of the microphone is brought after the preamplifier and the first gain stage, and then it comes to a mixer. Right now in the studio also we have a very professional mixer at the rear of the room, and it is managed by professionals, where you could mix different types of signals in the way you want. Now in a public address system you would see right in the front panel a console by which you could choose either from a cassette recorder or from microphone, or you could even mix things. Now therefore in a public address system, the third stage would be another kind of a gain stage, where the gain need not be very high, maybe somewhere between 10 to 100, and that gain also, as we all know, can be controlled from outside. And again, as we know, the mic gain also can be controlled from outside. And then finally you have a output stage which is a power amplifier. My last lecture will be on power amplifier, where we will talk about the specific requirements of an output stage. Now in the case of a public address system as compared to an op-amp, the scenario is very different. In an op-amp, the load you are talking about is only about 20 milliamps, which is very, very small. Whereas in a public address system, the load have to cater to extremely low resistances, or in fact very high currents. Now the requirement may be anywhere from 10 watts to 100 watts, very high power requirement. Therefore, as we all might have noticed, if you look behind a public address system, you would see power transistors put there with heat sink. Anyway, coming back to our topic of multi-stage amplifier. So we saw in a actual practical application like a public address system also, we have the case of a multi-stage amplifier, where we have 3 or 4 or more stages. Each one is chosen with a particular purpose. Now let us take an example, a numerical example, to illustrate what we are talking about. Now what we have here is basically the equivalent circuit of a multi-stage amplifier, in fact stage by stage. Now this particular multi-stage amplifier has an input which is fed by a source Vs, and the source resistance is fairly high, 50 kilo ohms, and that feeds to the first stage. Now the first stage amplifier input resistance is 1 mega ohm, and the gain, the open loop gain, rather the without load, the gain is 10, and it has a source a internal resistance or output resistance of 2 kilo ohms. Now the output of the first stage is connected to the second stage, which has an input resistance of 50 kilo ohms. Now that particular second stage has an open voltage gain of 100, and the output resistance is 1 kilo ohm. Now this particular output of this second stage is fed to the third stage, which is essentially has an input resistance of 5 kilo ohms and an output resistance of 20 ohms, but the gain of that particular stage, voltage gain of that particular stage, is just unity, and then the output of the third stage is connected to the load. Now let us try to analyze this, how this particular amplifier works and how it has been chosen. As I just now said about the examples of both op-amp and a public address system, we see a lot of similarity between what we said and also in this particular example. We see that the input is from a sensor which has very high output, the source resistance, which is about 50 kilo ohms. It may be higher, 100 kilo ohms, it could be even higher. Now, as we said, the first stage, we saw that in the both the previous examples, that the first stage must have very high input resistance. This particular stage has an input resistance of 1 mega ohm. So, that satisfies that condition, but the gain is not that high. The voltage gain is only about 10 without load. Now, the second stage, if you see, the input resistance is not high. Compare the input resistance of the second stage with the input resistance of the first stage. First stage had 1 mega ohm, whereas the second stage has only 50 kilo ohms. But this stage has 10 times the gain of the first stage. First stage only had a gain of 10, but this stage has a voltage gain of 100. Now, the output resistance of this stage is roughly, let us say, almost comparable with that of the first stage. Now, when we come to the third stage, which is the output stage, we see that the input resistance is still smaller. It is only 5 kilo ohms, in fact the smallest of all the three. But look at the output resistance of this stage. This stage has 20 ohms, which is the smallest again of all the three stages, and this then drives a load which is 50 ohms. Let us analyze this circuit and let us see it stage by stage. Let us see the voltage gain stage by stage. Now, what the way we would do is, we would look at the gain of the first stage and then as the Vi2 by Vi1, and then we would see Vi3 by Vi2, and then finally we will see VL by Vi3. So, let us do this step by step. Now, in the first stage, since we have the source also, if you look at the fraction of the voltage which is appearing at the input of the first stage, that we can find the fraction as Vi1, which is the voltage at the input of the first stage, divided by Vs, which you would find as 1 mega ohm by 1 mega ohm plus 50 ohm, and that you would get as 0.952. So, it is less than 1. Now, the voltage gain, the first voltage gain, as I said, is measured from the output of the first stage to the input of the first stage. Now, one very important thing to keep it in mind when you talk about a multi-stage amplifier is, the load of the first stage is actually the input resistance of the second stage. The load of the second stage is nothing but the input resistance of the third stage, and so on. So, if we calculate the voltage gain, we see that the open circuit voltage gain was 10, and 10 multiplied by 50k, this is the input resistance of the next stage, by 50k plus 2k, and we get that as 9.615. So, the open circuit gain was 10. Now, because of this finite output resistance, we see that the gain drops to about 9.6. Now, let us come to the stage 2. The voltage gain of the second stage can be calculated as from the output of the second stage to the input. So, at the output, this particular voltage Vi3 is developing across the input resistance of the third stage, and this is the Vi2 is at the input of the second stage. Now, as we said, the second stage has fairly high gain, a gain of 100, open circuit gain of 100. Now, here the load in this case is the input resistance of the third stage, and that is 5 kilo ohms, and this stage has a output resistance of 1k. Therefore, the voltage gain would be 100 into 5k divided by 5k plus 1k, that comes to 83.33. Now, coming to the third stage, we said the third stage is primarily the output stage, therefore, it does not have any voltage gain. The open circuit voltage gain is only unity. Now, this particular stage had an output resistance of 20 ohms and the load was 50. Therefore, the voltage gain of the third stage would be 50 divided by 50 plus 20, that comes to 0.714. Now, if we calculate the total gain of the 3 stages and if we call it as AV, this will be nothing but from VL, it will be VL divided by VI1. VL is the voltage developed across the load, VI1 is the voltage at the input to the first stage. So, we would see that that is nothing but the product of the 3 voltage gains we just now computed, AV1 plus into AV2 into AV3. Now, if you do the calculations, you will get that to be approximately 572. Now, what is also important is the voltage gain from source to load. Yesterday we used the term overall voltage gain. Now, in this case the overall voltage gain would be the fraction VL by Vs, where VL is the load voltage across the load, Vs is the voltage across this voltage, the output, the open circuit voltage of the source. So, that would be nothing but VL by VI1, which is nothing but the fraction of the voltage developed at the input of the first stage, times VI1 by Vs. Now, this we would find as will be nothing but the voltage gain times the fraction of VI1 by Vs. So, if we do the computation, we will see that drops to 544. So, if you see that without that fraction, so if we had the input resistance, if it were infinite, then AV and the overall voltage gain would have been same, but here the input resistance being only 1 mega ohm, we see it drops. So, higher the input resistance for the first stage, the closer these two numbers would be. So, this is a very good example to illustrate what we are talking. Let us also compute the current gain and also the power gain. Now, the current gain can be defined as the current I naught, which is the current flowing into the load, divided by current II, which is the current flowing into the first stage. Now, we know that I naught is nothing but the voltage VL divided by the load, which is 50 ohms, and the input current is nothing but the voltage across the input first stage divided by that resistance. So, this we would see that by, if you compute this, you would come to be 2 into 10 power 4 times the voltage gain, and that comes to 11.44 10 power 6, fairly high current gain. Now, the power gain is again calculated as the power PL divided by PI. Now, PL, the power delivered to the load, is VL into I naught, and PI is I1 into II, which, so this would be nothing but the product of the voltage gain and the current gain, and this happens to be an extremely large number, 6.54 into 10 power 9. Now, we need to notice a few points. Again, to reiterate, what we saw was that if we want to avoid losing signal strength at the input end, the first stage should have fairly high input resistance or the order of 1 mega ohm or higher. This resistance, the input resistance of the first stage, should be much higher than the source resistance. But one very important thing to keep it in mind is that the gain need not be high. Coming to the second stage need not have high input resistance, but it must have large voltage gain. Coming to the third stage is not required to have any voltage gain, but it should work like a buffer amplifier. So, it should have reasonably high input resistance and definitely low output resistance, and the output resistance must be much smaller than the load. So, this is what we saw from the amplifier. Now, here we have the 3-stage multi-stage amplifier we considered. Now we could combine the entire thing in by the equivalent circuit of a voltage amplifier, which would be more useful for us ultimately. Now that we can do by, we know that the equivalent circuit of a voltage amplifier would have a resistance at the input, which is the input resistance, and then the output side you would have a controlled voltage source, which would give you the open circuit gain times the input voltage, and then you would have the source resistance. That is the equivalent circuit of a voltage amplifier. In this case, the input resistance happens to be the input resistance of the first stage. Now the source and the load we have kept apart. So we have kept this particular amplifier as one block. Now the gain here, coming to the output resistance is nothing but the output resistance of the last stage, which is 20 ohms, and the gain we have here is the product of the two gains, the first and the second stage. So in this case you would see that we can represent what we considered earlier. After we do the computation, we can show it by a very small, very simple voltage amplifier circuit, which combines all that, which is essentially having a 1 mega ohm input resistance and having a voltage gain of 800 roughly, and having an output resistance of 20 ohm. So when we connect this, when we use this for a particular application, we can see what kind of gains we will get by just connecting the source and the load. Let us compare this. Now in summary, the purpose of a multi-stage amplifier is to then maximize the advantages of the individual stages and to minimize the shortcomings of the stages, so that overall amplifier specification would be what we want. So we try to, so therefore the placement of the individual stages is very important. What we have here is the equivalent circuit, the open loop equivalent circuit of a 741 op amp. Now a 741 op amp, the input resistance is 1 mega ohm, the open loop gain is 2 into 10 power 5, and the open loop output resistance R naught is 75 ohms. So we see a lot of similarity between what we considered in the previous numerical example and what we saw here, except for the numbers, some of the numbers. Now therefore let us see how do we, what kind of a strategy should we use when we talk about designing or choosing a multi-stage amplifier. Now one of the first things we need to do is to looking at the specifications, depending on the kind of gain required or maybe the power, the load requirement and so on, we need to decide whether we would have 2 or more. In any case we would need 2 stages. Now typically in a multi-stage amplifier you might have as many as 3 or 4. Generally typically you may not have more than 4 stages. Now as I said, it is extremely important to choose stages as required and also as they need to be arranged in the correct order. So it is all about maximizing the advantages of each stage which we studied and minimizing the disadvantages. And then we said what we do is you could express each individual stage by its equivalent circuit. Now again the analysis of a multi-stage amplifier occasionally would be quite involved, especially if you look at the inside circuit of a 741 op amp. It is extremely tough. It has about 27 transistors, and the amplifiers used there are very different from the amplifiers which we studied. The amplifiers which we studied, common emitter amplifier and common base and common collector, they all were discrete amplifiers. Now discrete amplifiers have a very major disadvantage. The major disadvantage being there is a kind of upper limit on the gain you can get. typically you cannot get more than about say gain of 100 from a discrete amplifier, typically maybe you could get maximum 200, beyond 200 is almost impossible. Whereas when you talk about an IC amplifier, you can get gains of the order of 1000 easily. This is done by using active loads, and some of these things were covered and will also be covered maybe in some other lectures. Now in an IC amplifier you would use a current source itself as the load. Now we know that a current source has extremely high output resistance. So a current source if I use as a load, then I am getting a very high load which would give me a very high gain. So if you look at a 741 op amp inside, you would see that you won't find loads being used as resistors, and all the loads are active loads. And also in an IC amplifier the biasing is entirely done through current sources. This is for the simple reason that if you change the power supply, the biasing does not change. This is very different compared to what we are familiar with. We know that in a discrete amplifier, if we change, and when we design a discrete amplifier, we start with the power supply available. Now if you change the power supply value, we would see that the biasing will all change, and if we let us say change it by 50%, the operating point would shift drastically. Whereas in an IC amplifier this is not the scenario. A 741 op amp can be used from all the way from plus minus 6 volts to plus minus 18 volts 3 times. This is impossible in the case of a discrete amplifier. Now this is possible in a 741 op amp because of the way it is biased through current sources. Now coming back to the example of 741, even though it is so complex, the way you would analyze the 741 op amp is to split the entire IC into 3 stages. The first stage would be the input stage, which is a differential stage. The second stage is a gain stage, and the third stage is an output stage. So the way when we analyze a 741 op amp, what is always done is to isolate these stages, and then for each of the stages you would express that stage with its equivalent circuit, and it may not be always possible to express it as a voltage amplifier equivalent circuit, and very often you would use a transconductance amplifier model. And once you combine these 3 stages, the equivalent circuit of the 3 stages in a 741 op amp, the extremely complex circuit becomes a very simple block as we saw earlier. So the strategy in analyzing a multistage amplifier is to first of all to divide the multistage amplifier into stages, the logical stages, and then to express these individual stages by the equivalent circuits, and the stages might maybe of different amplifier types. As I said, you may not be able to have a voltage amplifier equivalent circuit. So depending on what kind of is convenient from the analysis point of view, we could do this. Now in a course like basic electronics, this kind of analysis, detailed analysis may not be required, but what is important is basically the concepts involved in this. So once we understand the concept of a multistage amplifier, that it consists of more than one stage, each stage having its own different parameters, and a multistage amplifier has a cascade of 2 or 3 stages, then the analysis becomes much simpler. Now let us come to some actual applications and some realizations. Now when we talk about BJTs, we talked about 3 types of amplifiers, and we know that common emitter, common base and common collector have very different performance parameters. Now let us try to compare them. before we look at the way how we could pair them. Now, so let us classify them, the type of the amplifier, and let us write about the input resistance. Let us talk about the output resistance of these and the voltage gain. Now, if you look at a common emitter amplifier, we know that the input resistance, yesterday we saw that is typically R pi, and we said R pi is at the order of a few kilo ohms, it is not very high. So, let us write let us say low to medium. So, this meaning at best you could get a few kilo ohms, not hundreds of kilo ohms. Now, coming to the output resistance of a common emitter amplifier, we saw that the output resistance is approximately the collector load resistance, which is maybe definitely in the order of kilo ohms. So, from the output resistance point of view, it's, let us say that it is high. So, it is definitely in the kilo ohms range. So, let us say it is high. Now, the voltage gain we know is much greater than unity. So, typically we talk about a common emitter amplifier having a gain of let us say 100 or so. Now, when we talk about the common base, which is considered yesterday, just briefly, we said the input resistance is very low. Now, the output resistance we said is same as that of the common emitter, and the voltage gain also we said is the same as that as the gain. Typically, if you use the same components, you would find the gain to be the same as that of the common emitter, with the exception that the sign, there is no phase inversion. Now, when we talk about the common collector, which is nothing but the emitter follower, we know that the input resistance is high. In fact, we can make it as high as possible by choosing different values of the emitter resistance. Now, we also know that an emitter follower is nothing but a buffer, therefore, the output resistance is low. That is why we use an emitter follower as a buffer, and we know that the voltage gain of a emitter follower is approximately 1. Now, we need to keep this in mind, this picture in mind, when we talk about pairings, when we talk about pairing BJT amplifiers. Now, before we do that, let us look at one very interesting and very useful pairing, which is what is called the Darlington configuration. Now, you can think of in a Darlington configuration, what is done is you are essentially cascading two BJTs by connecting the emitter of the first BJT to the base or the second BJT, connecting the collectors of both the BJTs together, and then taking the output from the second emitter. So, if you consider the Darlington configuration as though it were a single BJT, then you could think of the base terminal of this compound device being that of the input of the first transistor, the collector they are common, and the emitter terminal of this compound device being the emitter terminal of the second device. Now, here, as we know, because of this the way we connected it, the base current of the first stage gets multiplied by beta plus 1, let us say approximately equal to beta 1. Now, the emitter current, that would be the emitter current of the first stage, and that flows as the base current of the second stage. Now, if we come to the emitter current of the second stage, we can say that when we compare the emitter current of the second stage or the emitter current of the compound device, we see that the emitter current would be beta 1 times beta 2 times IB1. So, if we talk about a device where the betas are same, we are talking about getting a device where the beta gets multiplied. So, if you talk about let us say a transistor having a beta of 100, we are talking about by connecting this kind of a device in a Darlington configuration, we can think of having a BJT having a beta of 10 power 4, which is extremely high. Now, this kind of Darlington configuration is very common and it has very useful purposes. Now, when you talk about the application of a Darlington, one of the first thing is to think about, let us say, getting high beta from a transistor. Now, the major application of a Darlington configuration is to use it as an emitter follower. Now, in an emitter follower, we said that the output resistance is low and the input resistance is high, and in our yesterday's discussion we said that the input resistance of a single stage BJT, single stage common collector amplifier, is approximately beta times the series resistance at the emitter of the emitter follower. Now, if in place of the single stage, if we use a multi-stage, that a compound device, we get a high performance emitter follower as what is shown here. So, in this emitter follower, what we have done is, we instead of connecting a single BJT, we have used that compound device, which is a Darlington configuration. With the result, the input resistance at the seen by the source would be, if with the same device, if we have the same device, you can say it would be beta square times Re, or let us say beta 1 times beta 2 Re. So, this can be extremely high. If you take a number, say Re, if you take Re to be, let us say 1 kilo, then we are talking about getting an input resistance of beta square times 1 kilo, which is 10 power 4 times 1k, very high. Now, by changing Re, we can get much higher values. Now, another advantage of the Darlington configuration is, because of this, the output resistance now becomes extremely low. In a single stage emitter follower, the output resistance may be typically the order of a few ohms or maybe few tens of ohms. In this case, we could get extremely low, maybe an ohm or less, much less, and the gain would be in this case much closer to unity compared to the previous case. So, a Darlington configuration is an extremely popular configuration, and it is used to get a high performance emitter follower. We need to see this in the context of a voltage follower. We know that in an op amp, if you consider the non-inverting configuration, if you directly connect without any resistance, if you connect the output through a wire to the negative terminal, and if you apply the input to the positive terminal, we have a voltage follower. In a op amp voltage follower, the input resistance is extremely high, it would be hundreds of megohms, at least theoretically. Now, we need to compare the performance of a high performance emitter follower in the lines of a voltage follower. We would see that we may not get anywhere near there, but still the performance of the emitter follower with a Darlington configuration would be much higher than that of a single stage. Now, when we use a Darlington configuration, we need to keep a few things in mind. One very important thing is to see about the beta of the individual transistors. We assume that if you make a Darlington configuration, we assume that the compound device we said would have a beta of beta 1 times beta 2. Now, we know from our study of BJTs that the current gain beta is a function of the collector current. Now, when a manufacturer makes a transistor, and in a data sheet the manufacturer would always specify a kind of recommended current, and most of the parameters would be measured at a particular collector current. So, we know that in a BJT the beta would increase with collector current, and especially if you have very low collector currents, the beta would be much smaller. Now, in a Darlington configuration we can get into trouble. What can happen is, think about the previous scenario where we had a configuration like what we had, a simple cascade. Now, here in case we have a large resistance, let us say that we want to somehow get, let us say, tens of megohms from a Darlington emitter follower. So, therefore, let us say that we put a large resistance at the emitter to get an emitter follower, and let us say we put say 100 kilo ohms or let us say 1 megohm. Now, what would happen is the current of the say Q2, the IC of Q2 would be, let us say, if it is let us say 1 milliamp or let us say 0.5 milliamp. Now, the collector current of the first BJT would be less by a factor of 100, and what would happen is at that kind of collector currents, which is in the microamp regime, you would see that the beta would drop drastically. Therefore, even though we assumed the compound device to have the same beta, assuming the same device, but in actual situation the beta 1 would be much smaller. So, this is a very troublesome situation, and we need to have a solution for this. Now, the solution is to introduce a resistor after the first stage and connect it appropriately. Now, in an IC kind of a amplifier or in a situation, it will be best to put a current source here, but in a discrete amplifier it may be difficult to have a current source. So, we could put a resistor here. Now, this resistor need to be chosen very carefully. This resistance is chosen such that you have a certain amount of base current, certain amount of emitter current here. Now, the current flowing through this particular resistor is chosen such that the beta of the first transistor does not fall drastically, so that we can still continue with the assumption we had that the total overall beta would be beta 1 times beta 2. So, this is something we need to keep in mind when we talk about a Darlington, when we design an actual Darlington, and if we try to increase the input resistance by putting a large resistance at the emitter of the second device. So, we need to be very careful about the biasing. We need to ensure that both the transistors have reasonable currents. Now, let us consider a typical discrete multi-stage amplifier. Now, what we have here is an interesting multi-stage amplifier, which is nothing but a cascade of two common emitter stages. What we have here, the input, the first stage is the standard common emitter amplifier which we considered yesterday, and this is an emitter bypassed common emitter amplifier, and everything looks very familiar. But the second stage uses a PNP transistor, and here also the emitter is bypassed and you are taking the output from the collector. Now, it is very common to in multi-stage amplifiers to use PNP transistors. Now, PNP transistors are you can be cascaded with NPN in a fashion like this. Now, one of the things which we need to keep it in mind is the analysis of this kind of multi-stage amplifiers. Now, this here we have two common emitter amplifiers. So, the AC analysis we could again, just like we said the strategy, we could split this into two common emitter, and we could consider this as a cascade of two common emitter amplifiers, and then we would be able to solve this. However, we need to also be concerned before we do the AC analysis, we need to get the biasing currents correctly. Now this particular circuit is a bit tricky. Let us see how we would analyze a circuit like this. Now what we have here, we know that in the first stage is fairly easy. The way we analyze a common emitter amplifier is we convert the input side into, we disconnect the source, we convert the input side into a Thevenin equivalent, and we get a VBB. That VBB would be nothing but VCC times R2 by R1 R2, and then the Thevenin resistance would be RB, which is nothing but R1 parallel R2. Once we do that in the common emitter amplifier, we can apply KVL in the common in this particular loop. So here once we replace the input side by the Thevenin equivalent, a voltage source and the Thevenin resistance there, we can apply KVL here and get the base current. Now once we get the base current here, now assuming this to be active region, we can get the collector current. Now in this particular amplifier circuit, the circuit is a bit tricky. The collector current IC1 has two components. One component is the current flowing from through the first the RC1 resistance here, which we can call as IR1, and the second component is the current flowing from the base towards the collector. Mind you, this is a PNP transistor, therefore the direction of current, base current would be outward. In an NPN, the direction of the base current would be inward. So how do we solve this kind of a situation? Now here what we need to do is we need to write a simple equation. Now let us see how we can solve this. Now we can write an equation for IE2, the emitter current of the second amplifier, as VCC minus VE divided by RE2. Now VE, which is the emitter voltage here, is nothing but the collector voltage of the first transistor plus VBE. Mind you, this is a PNP transistor, therefore the emitter would be more positive than the base. So we get an equation here for the IE1. Now once we get an equation for IE1, we can divide that by beta plus 1 to get IB2. Now we saw that this particular expression has the term VC1, which is the collector potential here. Now VC1 we know is nothing but, or rather we can write IR1 as VCC minus VC1 by RC1. So now we have expressions for both IR1 and IB2 involving IC1. Now we know the value of IC1 because we calculated IB1. So from this we can solve easily for VC1, which is the collector voltage. The moment we get collector voltage here, we can immediately find out the emitter voltage here by adding VB voltage to that voltage, and then we get the emitter current here. So that way all the biasing currents can be found out and all the small signal parameters can be found out. So most of the discrete amplifiers, multistage amplifiers, would have this kind of a connection. Now you can also, in this case actually we see that they are cascaded. You can think of this as a direct coupled. Now you can also think of two stages like common emitter or common base or common collector being kind of isolated from each other through a capacitor. Now that way you could consider them much easier because each stage then would be independent.